All right. Um, Good evening, all. Welcome back to the second week of TA Live sessions for AI SMPS. So, yeah. So first things first. Um, so you can feel free to switch off your videos. Uh, that will be fine, and that will also help keep the length of the video recording, size of the video recording lesser. So yeah, if you are comfortable, please feel free to switch off your videos. Although if you have any doubts at any point during the live session, you can feel free to unmute yourself and speak up. Okay. So yeah, welcome back to the second week, and today we'll be discussing some questions from week 2 of the course content. And are there any doubts related to the live sessions in general? I think I covered most of the points in the previous live session, which was the first live session, about what you can expect from the live session itself. But yeah, if you still have any pending doubts, feel free to let me know before we get started. Is the extra noise still there, Raj? Is it better now? Okay, is the audio clear for everyone, or is it only for a couple of people that it's not clear? Okay, it seems like it's clear for everyone. Can you just confirm if the screen is visible? Cool, thanks for confirming. Yeah, so just to clarify one doubt that's been raised in the chat box, where do we upload the recordings? So I'll just show it to you. I also showed it to you in the last class, but let me just revisit it. So if you log into your Swayam portal, right, you'll have a section on problem solving session. So just click over there and use this link. Click here, it will lead you to a Google Sheet. There you'll have access to both my live session as well as the live session recordings of the other PMRFTA who is conducting the live sessions on Saturday, I think. So yeah, you can use that to your advantage. Okay then, let's get started for today. And okay, so today we are going to discuss two of the most well-known and simple methods that we start with, heuristic for uh, breadth first search and depth first search. Okay, so broadly, our goal is to start from one of the nodes in this graph, okay, and reach one of the nodes, one of the other nodes in this graph, which is the goal node. Okay, and this graph shown over here basically tells us which nodes are connected to whom, and this table over here on the left tells us which nodes can we go to from a given node. Okay, for example, so from S we can go to C, A and B in that order, right? So you can see S is connected to C, A and B. Similarly, A is connected to D, B, S and E, right? So from A we can go to B, E, D and S. Now there's a reason why this is mentioned as C, A, B and B, E, D, S and not in an alphabetical order, because that is the that is the order that we are telling we will follow whenever we encounter a particular node and we want to move from that node to another node. Okay, so when we are at a particular node and we have a choice to go to multiple possible nodes in multiple possible directions, we have to choose one among them, right? And once we have multiple choices, we have to make a decision on where to go, and depending on the heuristic that we are using, we are going to make a choice, and this particular order that we are given is going to help us in making that decision. Okay, so is the problem setting clear? Any doubts on the problem setting? Okay, if not, then that's great. So let's go to the first question then. Okay, so the first question tells us identify the DFS search tree. Okay, so assume that S is the starting node and your goal node is G. Okay, and based on this graph and the move gen table that is given over here, which of these four trees do you think would be the correct search tree when we apply DFS or a depth first search? Okay, so how many of you are familiar with the depth first search algorithm? Yeah, I see a couple of hands raised. You can feel free to unmute yourself if you have any questions, or you can also write down any feedback or anything you want to say in the chat box itself. Okay, so a couple of you are familiar, so that's great. Um, I'll let you try to figure out the solution to this particular problem, and then after a couple of minutes, we will discuss the solution. Sure, we will discuss the solution, but I'll first give you a couple of minutes to try to figure out the answer to this question on your own. Yeah, hi, welcome all. Welcome to the new joinees. Once again, I'd like to say that you can feel free to switch off your videos. That is completely fine with me. Um, okay, so there are a couple of answers. Some people say it's option A, some people say it's option D, and some people also say it's option C. So let's see. Let's go back to the question and see which of these answers could be correct ones. So, okay, some basic questions. So, both DFS and BFS, they use certain specific data structures. So, which data structure does DFS use? Does anyone know? That's great. That's correct. It uses a stack. Yes, once again, I'd like to say you can please switch off your videos. That will help us keep the size of the video recording smaller. Okay. Yeah, please switch off your videos. Prakash, it would be great if you could switch off your videos, and others as well. Okay, great then. Okay, yeah, so stack is a data structure that DFS follows. So let's look at which one of these is the correct option. So as the name suggests, in a depth first search, we start from a particular start node, and then we choose a particular node to go, and then we follow a particular depth in a particular direction, right? And that's what the name of the algorithm suggests, and we use a stack for this purpose. The way DFS does this is by using two lists. One is called an open list and one is called a closed list. Okay, so what happens in an open list is when you are at a particular node, okay, let's say you are exploring a particular node, then the nodes that you could go to from this node will be added to your open list, and this will be a stack. Okay, and then your closed list would contain a list of those nodes that have been already explored. Okay, so when you are starting out, your open list would consists of both open and closed list would be empty, right? Let me write it out for you. So let's say this is your open list, okay, and this is your closed list, and both of these are sorry, empty to begin with. Now what we'll start is we'll add S to the open list, right? Because S is our starting node, okay? S is our starting node, right? Now which are the nodes that we could go to from S? C is one of the nodes, A is one of the nodes, and B is one of the nodes, right? C, A, B, that's right. So what we'll do is we'll add C, A, B to our open list in that particular order, okay? And remember, we have already explored S, right? So S will go into our closed list, okay? Cool. Then now, because this is a stack, okay, which of these elements will be explored next? C, that's correct. So the element that will be explored next would be C, and we will look at which are the nodes that we could go to from C. So from C we could go to F, B and S, but B is already a part of the open list, so we don't need to add it again, and S is already a part of closed list, which means that S has already been explored, right? So the only thing we need to add is F. So what we will do is we will add F at the beginning of the list because this is a stack, and C will go into our closed list, okay? Now so it'll look something like this, okay? Now which is the node that we are going to explore next? F, that's right. So you see we went from S to C to F, okay? So till this point tree 1, tree 4 are similar, right? Tree 2 and tree 3 we know that they are incorrect because we have not explored A and B, right? So we can eliminate tree 2 and tree 3. We know that the correct option is among tree 1 and tree 4, okay? So after F, where will we go? Let's look at where we can go from F, okay? So from F we can go to B, but B is already part of the open list, right? We can go to E, that is correct. We can go to D, that is also correct. We can go to C, but C is already part of the closed list, right? So we don't need to consider that. We can go to H. So the elements we can go to are E, D and H in that order, okay? So we will add E, D and H to our open list, and we will add F to our closed list, right? Is it clear until this point? Okay, that's great. So now what do you think? Which of these options, tree 1 or tree 4, would be correct? That's right. So as many of you suggest, it would be option D. Right, let's complete our algorithm for the sake of completeness, right? So now E is at the head of the list, right? So we will explore E next. Okay, so from E, where could
I have one question in this.
yeah, Rahul, please go ahead.
Can you show me again
This one.
that? Yes. Why not HDE? Why EDH?
Because that is the order in which we are given the moveGen function. Okay, so if you remember, I just mentioned before we started the question that we are given this table to tell us when we are at a particular node, we can go to different nodes from this node in some particular order, right? And that order is given to us beforehand, right? That is why, because this appear in E, D and H, this order in this moveGen function itself, that's why we are assuming, we are inserting these elements in that fashion in the stack. Okay,
But in stacking first, he will put E and then C and then H at the first. It is analyzing first E.
no, no, don't think of it in that way. It will be inserted such that this order is maintained. Okay, so first H is inserted, then D, and then E. The point is to maintain the order. Okay, in case the moveGen function is not given to you, then you have to explore what are the different ways in which these could be inserted into the stack. Okay, based on that, you could have several different search trees. Okay, exactly. That's right. See, in this question, we are not told that we have to maintain an alphabetical order, right? That's we are not even think. That's why we are not even thinking about alphabetical order. We are given a moveGen function. We have to follow whatever the moveGen function says. Okay, so if we are at F, okay, we will look at which are the nodes we could go to from F. Okay, and those are B, E, D, C, and H. Okay. Yes, 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 exactly. Exactly. And out of these,
Sir, do you mean that the constraints would be taken after that, no?
you could think of these as constraint, yes. Yeah, yes. And we also need to see which of these are already part of open and closed list, right? So because when we were at F, B and C were already part of open and closed list respectively, right? So we don't need to insert it back again into the open list. Okay. Okay, cool then. Now let's look at, so we were at E now, right? So where could we go to from E? We could go to A, D, H and F. Now out of these, A is already in the open list, D is also already in the open list, H is also already in the open list, and F is also in the closed list, right? So what will we do? Exactly. So we don't need to add anything else in this step to the open list. We will just remove E and add it to the closed list. Yeah. So we had E at the beginning, right? But we saw that once we are at E, we cannot add any new elements to the open list. So we will just simply pop out E. We will have D, H, A, B remaining, and we will add E to our closed list. Now we have to explore D. Okay. So you see, tree 4 suggests that after F we explored E. After E we will explore D, right? And we will see why T4 is correct, right? So once we explore D, let's look at which are the elements we could go to. we could go to F, E and A. But again, F is part of the closed list, E is part of the closed list, and A is already part of the open list, right? So no new element to add to the open list. So we will repeat the same process. We will simply pop out D and nothing else will be added. So we will have HAB in the open list and T will get added to the closed list. Okay, next we will explore H. So from H, where could we go? We could go to F, E, I, J and G. Okay, so F is already part of the closed list, E is already part of the closed list, I is new, right? J is new and G is new, right? So which of these elements will we add to the stack? Exactly, I, J and G. So let's do that. Let's remove H and add I, J and G to the stack, followed by exactly. And let's also add yes, H, T, E, F, C, S. This is our closed list. Next we will look at I. Okay, so let's go back to the figure. So when we are at I, we could go to H and J, but both these are already part of the closed and open lists, right? So nothing new to add, so we will simply pop out I. So we will have J, G, A, B remaining, and in the closed list we will have I, H, D, E, F, C and S. Okay, yeah, so this is how it will look like. And to verify whether we are still following tree 4, let's have a look. So we first explored S, then we explored C, then we explored F, then we explored E, then T, then H, then I, and now we are going to explore J. Okay, so from J, where could we go? We could go to H, I and G. Yeah, but H and I are already part of the closed list and G is already part. G is already there in the open list, so again nothing new to add, right? So nothing new to add, so we will simply pop out J. So we have G, A and B, and in the closed list we are going to add exactly. This will be our closed list. Now we are exploring the G node, which is our goal node, right? So we have reached the goal node, so we will stop our algorithm over here. We have reached the goal node from the start node. So let's go back to the figure. So now after exploring J, we reach the G node and we stop our search. So finally this is the tree that results in our DFS search tree. Okay, so the correct option would be tree 4. Mm-hmm. Yeah. That is right. If G was not our goal node, then we would have continued this process. But since we are already at the goal node, we don't need to think about where we could go to from G, right? So even though we have we have A and B still remaining in the open list, right? But we don't even need to worry about that because we already have reached our goal, which is G. Okay, so we can. Mm-hmm. Exactly. Yes. Not just in DFS, even in BF, even in breadth first search. So our the whole right. We will in breadth first search, you are right. Breadth first search uses a queue structure, unlike a stack structure, right? So we will be adding from the end, but we will be removing from the front only. Okay, that is how a queue works, right? In stack, we will look at it. We will look at it how a breadth first search open and close list will be looking like. But is this DFS clear to everyone? Mm-hmm. Right. So you could see that we did some sort of um yeah. If we have to backtrack, then yeah, we have to follow the simple algorithm. But here in this case, we saw that there was no need, right? If we go back to the search tree, yeah. So suppose we reached some particular node. Let's say after reaching H, we didn't encounter G, right? So suppose this I, J, and G was not here. So and we could not go anywhere else after H. So essentially, what we'll do is we'll go back to exploring A, which is also what is being suggested by our open list, right? Suppose G was not part of this open list, then what we would have done, we would have gone back to A. So that would be some kind of a backtracking itself. Okay. Okay. So I hope this is clear. I'll just address some things in the chat box. So I see there's some discussion of WhatsApp groups. You are free to join any WhatsApp group, but I would just suggest that these are not official groups. So uh, just a small disclaimer that join these groups at your own risk. Okay. So the the official forum of discussion, like I also pointed out last time, is this discussion forum over here, right? So if you have any doubts related to the course, I would encourage you post to this particular discussion forum, and it will be addressed by the lead TA of the course, who is Bhaskaran sir. You see he has replied to many of these questions as well, right? So yeah, this is the official forum, but other than that, you are free to join any groups at your own risk. Okay. Cool then. So if this is clear, let's move on to the next question, which is to identify the breadth first search tree. Okay. So it's the same graph as the same moved in table, but the algorithm is different. Okay. Um, So again, I'll give you a couple of minutes to try to solve this question on your own, and after that we'll have a discussion about the solution. Okay, and remember, a breadth first search uses a queue structure instead of a stack structure. So to address one question in the chat, mostly we will be studying algorithms only in this course. You are encouraged to try to program or try to code these algorithms up by yourselves, but programming assignments as such will not be a part of this course. Okay, so just a clarification over there. You you are more than encouraged to try to code it up on your own. That will also help you improve your understanding of the algorithms, but you won't be asked question based on programming. Thanks for your answer. There are a couple of let's wait for a while to see whether that's correct. Okay. So yeah, So there are a couple of answers. Some say it's tree 3, some say it's tree 2. Let's have a look at which of them is correct. Okay, so let me go back to the screen and we'll create a new open and closed list. Okay, so we'll start with S again. And which are the nodes we could go to from S? Those would be C, A and B, right? And again we have to maintain the order, right, which is specified by the movegen function. So let's insert CAB into our queue. Okay, now in a queue, so consider this is a queue. Okay, we insert elements from the end but we exit elements from the front, right? Whereas in a stack we insert elements from the front and we also exit element from the front. Okay, so that's the basic difference between a stack and a queue, just as a refresher in case some of you might not be remembering or familiar with it. Okay, so now which node will be explored based on this small discussion that we had?
C.
Correct, it will be C. So let's we will explore C, and let's add S to our closed list. Okay, and let's see where we can go to from C. Okay, from C we can go to F, B and S, right? Out of this, B is already part of the open list, S is part of the closed list, so only thing we can add is F. But where will we add F? Will it be FAB or ABF?
ABF.
That's right, it will be AB and F because we are maintaining a queue structure. Okay, so let's add C to our closed list.
Sir, one doubt, sir.
Yeah.
When we are adding the new elements in closed list,
Mm-hmm.
both depth first search and breadth first search same thing. Means new element is added at the end. Means to in the right hand side, right, sir?
Depends on what data structure we are using for both lists. Okay, so so
Example here S comma C.
mm-hmm.
In depth first search also S comma C or C comma F.
So in depth first search, since we assume that we are using a stack for both open and closed list, I added all the new elements to the front itself. Okay, because we were using a stack. In
For closed list we have to consider that stack first element in the stack is correct.
yes, mostly we need it for the open, but we can assume that we will use it both for both open and closed unless otherwise specified by our question. Okay. Okay then. So here also we are assuming that we are using both queue for both open and closed list. Okay, so now we will explore A. Okay, so let's see where we can go to from A. Okay, so okay, just based on this fact alone, the open list that we have maintained till now, can you see which of these options is correct?
Option C.
Okay, but remember we first explored S, then we explored C. Okay, so in which of these three is C coming before? um, C is coming after exploring S. Remember we go in a left to right fashion.
Okay, so in that case option B.
Option B, right? Yeah, we already saw that um, option 3, which is tree 3, can't be correct, because after S we are exploring C, okay, which is there in tree 2, tree 1 and tree 4. Now we already know from the previous example that tree 4 is a search tree for depth first search, right? So we can eliminate tree 4 as well. So tree 3 also we eliminated, tree 4 also we eliminated. So our contention is between option C and option 1 and option 2, which is tree 1 and tree 2, right? Now let's look at which element we are going to explore next, which is A, right? Because we are going to explore A, we can see that A was not at all explored in tree 1, right? But A is being explored after C in tree 2, right? So that gives us a hint that tree 1 is incorrect and tree 2 is our correct solution. Okay, so in exams or assignments, you can use this trick. You don't even need to solve your whole algorithm to arrive at which answer is correct, right? Once you see after a certain step that certain options cannot be correct henceforth, you can stop there as well. You don't need to solve the whole algorithm. But for the sake of completeness, let us complete and verify ourselves that tree 2 is the correct solution. Okay, Rashid, I see your question. Let's complete the discussion on this question and then I'll get back to yours. Okay. Okay, so let's see what will happen as we explore A. Okay, so as we explore A, we can go to B, E, D and S. But B is already part of the open list. We can add E, we can add D, and S is part of the closed list, right? So we have to add E and D into our queue. So we will have B, F, E and D. And SCA will be our closed list. Okay, next we'll explore B. So in B, where can we go to? We can go to A, C, F and S, right? From B we can go to A, C, F and S. But A is already part of the closed list, right? C is already part of the closed list. S is already part of the closed list. The only node we can add is F. Oh, F is also already part of the open list. So we don't even need to think about it, right? We will simply remove B. So what will be remaining is F, E and D. Okay, so let's see if that was the order that is also maintained in the tree. So we had C first, we had S first, then C, then A, then B, right? And now we'll go to F, right? Because that is what the open list is suggesting us, right? So let's explore F. We know that E and D will be at the front, but let's see if anything gets added. So when we are at F, we could go to that's right. Out of that, B is already covered, E is already part of the open list. Is D part of the open list? Yes, D is also part of the open list. C is already covered. H can be added, right? So let's add H over here, and let's add F over here in our closed list. Now we will explore E. Okay, so let's go back to E, and from E we can go to A, D, H and F, right? A is covered, D is covered, H is covered, F is covered, right? So nothing more to do. Nothing is added over here, right? And we simply add E. Okay, next we explore D. Okay, from D we could go to F, E and A, right? But again, none of these, because all of these are already covered, so nothing changes. um, we have H in our open list, and we add D to our closed list. Okay, next we'll explore H and see what gets added. So from H we could go to F, E, I, J and G. Out of this, I and J can be added, I, J and G can be added, and all others are covered. F and E are covered, right? So we'll add I, J and G. Okay, this is what it look like. Next we will explore I. So from I we could go to H and J, both already covered, so nothing changes, right? We can go to H and J from I, and both are already covered. So let's simply, yes, that's correct. So let's add I to our closed list, and next J will be explored, and from J we could go to H, I and G. Again, all of these are covered, so nothing new to add, right? So only G will be left in the open list, and here we will add J. Now we are going to explore G, but G is our goal node, right? So we stop over here. We have reached the goal node, and the order that we maintained to reach over here was SCAP, FED, HIJ and then G, which is what is shown in tree 2, right? So the correct option is tree 2. I hope that was clear. I'll give you a couple of minutes to convince yourselves while I'll look at the question in the chat box. Yeah, Satish, please go ahead. Mm-hmm. That's right, yes. Mm-hmm. Mm-hmm. Th- that's perfectly correct. Which one? Depth first search. Okay, just give me a minute. Yes, this is the. Mm-hmm. Mm-hmm. That's right. That's right. That's right. Yeah, good observation. Yeah. Mm-hmm. Sure. Mm-hmm. Exactly. Yeah, it's something like that. Yeah. Okay. So we were over here, and let me just revisit the question. So in beam search for SAT, if the heuristic value of two neighbors is same, it says break tie basis on the labels of the candidates. Can you please tell us based on lexicographic order of the labels or something else? Okay, so I guess that should be specified in the question and how you would be breaking the ties. Um, let's do one thing. Let's discuss all the questions for today, and then I'll open the lecture slides that sir would have discussed in the course, and we can revisit this question. Okay. Mm, or in fact, let me do one thing, because the next question would be very similar to what we have discussed now. Okay, so let me just introduce that question, and then we can visit this beam search question. So in the next question, we are again given a state space and move gen. Okay, S is again the start node, G is again the goal node, but the graph is different and the move gen is different. Okay, and again you have to simulate depth first search and breadth first search. Okay, so the next few questions will be based on the algorithm and the steps as you go through depth first search and breadth first search. Okay, so I'll leave this on here for a while, and I'll let you try to solve it by hand yourselves. In the meantime, I'll address the question in the chat box. Okay, so let me open up that particular lecture. Rashid, can you tell me which particular lecture where did sir discuss beam searching? Sure, I'll also try to find it in the meantime. Mm-hmm. Is it part of week 3 maybe? Week 2 only? Okay. Okay, okay. I'll just share this tab for your reference. This lecture material should have, right, those slides, but I don't see them.
Sir, actually heuristic searches in week 3 only. So in week 2, sir discussed uninformed search.
I see, I see. Okay. Oh, did I close the screen share? Let me just share it again. Okay. Okay. Let me open the slides from there then. Okay. Thanks for sharing that. So here we are, right? Okay. So the solution space is a space of candidate solutions. That's right. A local search method generates the neighbors of a candidate by applying some perturbation to the given candidate. Okay. So here over here we have 10111010. Here we are tweaking one bit each, so that gives us the different neighbors, the 7 neighbors, 7 children. Okay, so beam search for SAT. So here basically your question was, so usually what we would do is, we would choose the one that is the highest score, right? So your question is, if there are multiple children with high scores, which one do we choose? Am I correct? Okay. Okay, but if you have width equals to 2, then you can choose both of them, right? So mm-hmm. I see, I see. Um, Let me think what could be done. So basically what we are trying to do is we are trying to go with the children that give us the maximum scores. Let's say three of these gave us maximum scores. um, we don't have any way, at least now, to see uh, which of choosing which of these two among three children would give us a more optimal solution later down the line, right? So I would say in that case probably we could go with any two of those three, unless we are specifically told in the question that let's choose only the leftmost two or the rightmost two or the central two or things like that, right? If we are told that in the question, then you would have to follow that. Otherwise it seems like we could choose any two of those, and depending on whether we finally reach a valid solution or not, we could then again go back and re-choose if the two selected options did not give us valid results. Does it make sense? Okay. 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 So then I'll let the deadline for week 3 pass. So I was not aware this is part of the assignment. So think about it, and I'll also think about it in the meantime. I'm not saying that I also have the answer readily available, uh, but yeah, let's discuss this once week 3 due date has passed. Is that okay? Okay. Okay, then let's go back to the questions that we had. Okay, then. So has anyone?
Sir,
Yes.
so can you please show the open list and close list of VFS?
Of the previous question.
Yeah.
So this was the open and closed list for breadth first search, and this was for depth first search. Okay, I hope that helps. Okay, coming back to this question over here. So was anyone able to find the depth first search and breadth first search solutions?
We are looking, sir. We need the model.
Sure, you can take a couple of more minutes.
No, I need the previous
The
question.
previous one.
Yes.
Okay, I'll leave it open, but
Depth first search.
yeah, this one is depth first search. Um, yeah, just remember that this is using a stack. Okay, when you're using depth first search, it's using a stack. So you add elements at the front in the order that you have to maintain, and then you remove elements from the front. You just follow that.
Okay, sir.
Okay, so let's wait for maybe 2 more minutes. Okay, so to address the question in the chat, um, so Purab and others who have just joined, I'll just quickly show you. Each week has a set of assignments, okay, set of practice assignments and a set of final assignments as well, okay. So there you can find out the questions, and there it'll also be having a due date, okay. So it's okay if you have joined now, but try to solve the assignments that are still having due date remaining, okay. So Professor Sharma, I see you have unmuted yourself. Did you have a doubt? Yeah. Okay. So if you have found the path from the from the start node to the goal node, that should be sufficient. Basically, what we'll need is the open list and the closed list at the different stages of the algorithm, and that will help us answer the next few questions. Okay. For example, the next question asks us, at the instance when BFS finds G, the closed list is what? Okay. So what are the contents of the closed list is what we are expected to tell.
So ideally, we're supposed to stop when we find the goal, right?
Exactly. So at that point of time, there might be some elements, or there would be some elements in the closed list, right? So this question just asks us to report that set of elements.
Okay, sir.
Yeah. So let's have a look at the solution. Okay. So it says that it's E, D, C, B, A, and S. Okay. and um, let's try to solve it. So let's open another open and close list. Is it? Let's check. So here we have E, D, C, B, A, and S, and this says S, A, C, right? If we go in reverse order, so this it's slightly different, right? Oh, okay. Oh, wait, are you saying this for DFS or BFS? So the question asks about breadth first search, not depth first search. Uh-huh. Okay. Okay, you mean whether this is whether this should be after S, you mean, is it? Like S, A, B, C, D, E. No, no, no. See, the question tells us once we find G, okay? When we find G, G would be part of the open list itself. So let's go back to the previous examples that we saw. When we encountered G, it was still in the open list, right? That's why we were at the stage where we were exploring G. But what were the elements of the closed list at that point is what is being asked over here. And notice one thing, here we had followed the system where closed list is also following a queue system, but in this question, even for a breadth first search, this is following a stack, right? Because S is at the end. So be careful when we are looking at solving the question. Look at the question and see whether it has mentioned you use a particular data structure for the closed list as well. Okay, for the open list we know that it will use a queue, but this question expects an answer where the closed list follows a stack. Okay, so you had both flavor of questions over here. So be careful about that. Just a gentle reminder. Okay, let's. Yeah. Mm-hmm. 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 Yeah. So it basically turns out to be whether you want to retrieve the elements in your closed list and whether you want to retrieve it in an efficient manner. Okay. So I'll explain with the help of an example. So suppose, let's go back to our DFS example. Okay. And um, here what you were doing is you were adding elements in a stack fashion, right? So S was at the last and then you were adding elements one by one to the front of it. Okay, so when we want to retrieve the elements, let's say we pop the elements from this closed list, a stack, one by one, we will have J, then I, then H, then D, then E, then F, then C, then S, right? So this reverse order will give us the elements visited in that particular fashion, right? If we maintain a queue, which we did in case of uh, in case of BFS, when we remove elements from here, we will remove again from the front, right? So it will give S, C, A, B, F, E, D, H, I, J. Okay, again this will also give us the list of elements visited, but we don't have to do a reverse of it. Okay, so it is just a matter of what do you want to, or how do you want to retrieve your elements from the closed list. Um, Implementation wise, yes, maintaining a stack requires an additional step, uh, because you have to reverse everything once you want to get the exact list of exact order of elements which you encountered to reach at your goal state. But yeah, it's up to you, and also I would say it's up to the question. So more importantly, up to the question. Does that help? uh, mm-hmm. Which one? This one? Yeah. Mm-hmm. 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 Yes. Mm-hmm. Then I would say look at whether the question tells you to write the answer in a specific order. Okay, because what I have experienced in the previous time that I have taken this course is that such fill in the blank type of questions are very character specific or character sensitive, right? So if you mention this answer in the reverse order, even if it is correct, it will point it out as incorrect and you won't get the points for that question. So either verify it in the discussion forum while you have time before the due date in the to specify the order in which you with which the question expects you to answer, or just look at whether the question itself mentions or gives you a hint about the order in which it expects you to answer. Does that help? Mm, so what I demonstrated is that when we were solving DFS, we were assuming both to be stack. When we were solving BFS, we assumed both to be queue. Okay, but in this question 3, this has assumed that closed is a stack, even though we had solved it assuming that the closed is also a queue. Okay, that's why I'm just pointing it out for your help. Just make sure through either the question itself sorry, or through the discussion forum, what is the order in which you are expected to write the answer. Okay, yeah. We don't have the tree for this one constructed, but let's try to solve it and let's see whether we can find the tree or not. In the meantime, I saw there was a hand raise. You can feel free to unmute yourself.
No, that was rectified. Thank you.
Okay, that's great. Okay, then let's go back over here. So here we have S in the open list, and so we solved one question assuming that BFS follows both queue for both open and close. Now let's assume that for open it's a queue and for closed it's a stack, just for the sake of demonstrating what it'll look like. Okay. Okay, then from S where could we go? From S we could go to A and B, right? So let's add the elements in that order. A and B, and we will add S to close list. Okay, next we will explore A. From A we could go to C and S. S is already in the close list, so we add C. And here, because we are following a stack, let's add A in the front. Okay, next we will explore B. So from B we could go to C, D and S. C is already part of the open list. D is something that we could add. S is part of the closed list. Okay, so we will add D. And here we will add B at the front, so it will be B, A and S. Next we will explore C. So from C we could go to E, A, D, B. A is already covered, right, as part of the closed list. D is already part of the open list, and B is part of the closed list. So we can add E and we can add only E, right? So let's add that. And here let's add, okay. Next we will explore D. So from D we could go to G, C and B. C and B are already covered. G is what we are going to add at the end, not at the front, because it's a queue, right? So here we will have D, C, B, A, S, right? Something like this. And next we will explore E. So from E we could go to F, C and G. C is already covered, G is already covered. F is what is remaining, so we will add F to the end of the queue. G and F. And here we add E at the beginning. Okay, next we will explore G, but we have already reached G, right? So we don't care about what is in the open list. We stop the algorithm, right? And at this point, what is the closed list? Using a stack, it is E, D, C, B, A and S, and that is what is shown over here. Does that help? Any doubts? Cool. Okay, sure. Let's try to draw the tree. So first we had S. Okay, from S we went to A, right? And we could go to A and B basically from S, right? Sorry about the horrible drawing, but bear with me. So A and B, okay. Let me mark by this the nodes that we have visited. Okay, so S we visited. After S we visited, yeah, we can number it, that's correct. Let's call this 1, let's call this 2. Okay, next we visited B, right? Okay, after we visited A, we also added C to the list, so we will add that in due course of time. But B over here, okay. Then from A we could go to which elements? From A we could go to C and S, okay. So we add C over here. We won't add S because S is already at the top of the tree, right? So after B we will explore C, right? So this will be 4. From C, where could we go? We could go to E, A, D, B, but out of those we are omitting some elements. We are only going to add E to the list, but before that T was also part of the open list, right? Which is what we could go to from B.
Sir,
Yeah.
after exploring A,
Mm-hmm.
we should go to B, isn't it?
That's we are doing, right? That's what we are doing. So after S we are going to B.
A.
1, 2, 3, right?
Okay.
Yeah. So if so this might be a common confusion that we don't need to connect the two nodes if we are going from one to the other necessarily. Okay, the connections would be based on the graph that is given to us, but the order that we visit them would be from left to right. If we also go back to the previous example, see here we visited S, then C, then A, then B, right? But we didn't connect C and A or A and B, right? So C is connected to F because that is what the graph dictates. Does that help? Good. Okay, then let's come back here. So then we visited D. Okay, after D, so remember we had added E also, right? E we could go to from which node? From C, right? So let's add it over here. And let's call it 6, right? So we visited S, A, B, C, D and E. Okay, and at this point we would also have added G, which comes from E again, right? It comes from E. So sorry about that. G. So this is what it something like this would be the search tree.
Sir, it's from D.
It's from
D.
G is from D. Okay, let us check that. Okay, okay. Yeah. So we encountered G when we first were exploring D, right? Before E. So you are correct. So this is incorrect. We will add G over here. Okay, thanks for that. Does that help?
Yes, sir.
Cool. So let's go back to the questions that we had. Okay, this was the question 3. Let's look at question 4 as well. At the instance when BFS finds G, the open list is G and F, right? We just saw when we encountered G, G and F were remaining in the open list, right? So GF is the correct solution. I hope that's clear. Let's go to the next question. Then here we are asked about the DFS, the closed list. When we find the goal node, what will be the previous question? Okay. Cool. So question 5 tells us when we follow depth first search instead of breadth first search, what will be the closed list when we encounter G? Okay, so for this one I am not going to draw the open and close list again because we already have it. Okay, so yeah, this is the depth first search open and close lists, and I'll just let you verify the solution. So to address a question in the chat, so for open list we are always fixed that depth first search will follow a stack and breadth first search will follow a queue. What we will do in case of a closed list is what will be dictated by the question. So here also open list is a stack, closed is also a stack in this particular solution. Okay, so I hope the solution is clear, right? What we do essentially here is we start with S. Okay, from S we could go to A and B, so we add it to the open list in that order. We add S to the closed list, then we explore A. From A we could go to C and S, so we add C to the beginning of the open list because we are using a stack, and we add A to the closed list. Okay, so CB forms our open list, then we explore C. After exploring C we add E and D, then we explore E, and then we add F and G to the open list, and finally when we explore F we add G to the open list, and then when we explore G we know that we have reached the goal node, so we end this algorithm. Okay, and at that point of time the closed list would be F, E, C, A and S. So the correct answer would be F, E, C, A and S. The closed list when DFS finds G is F, E, C, A, S. Okay, uh, I hope this was clear. The next question asks us what is the open list when DFS finds G, and if we go back to the solution here, this was G, D and B, right? So that is what we should expect, and that is what we are getting, G, D and B. Okay, so I hope that was also clear, and that brings us to an end of the questions for today.
Sir, will the all this be available in the Jamboard, sir?
uh, Jamboard is I wasn't planning to, but I can add it to the list, to the folder where the slides are added.
Sir? Okay.
Yeah.
Because in the account itself, there is one thing called Jamboard,
Uh-huh.
where the previous slides are all there, sir.
Right. So I'll do one thing. I'll download this Jamboard as a PDF and I'll add it to the folder where all the other slides for the different weeks are added.
Ah, okay. Thank you, sir. Thank you.
Okay. Yeah. Mm-hmm. 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 In that case, you can look at what is the order of the nodes in which we did the exploration, right? So the way we were able to figure out where G came from in that tree was we saw that when we explored the node D, that's when we added G to our open list, right? So uh, that's why we added G as a child of D instead of E. Okay. Mm-hmm. You can do that. You can maintain a separate list of parents that uh, each node is coming from. Mm-hmm. Yes, exactly. Yeah. So for small examples like this, it's relatively easier to figure out manually. But I agree, for large graphs, let's say there are hundreds or thousands of nodes in the graph, it would be difficult to maintain manually. So in that case, you can always maintain a separate list as well, to make sure you know which source, which parent each node is coming from. Yes, there is a hand raise. Any doubts there?
Yes, sir. I mean, this is completely out of this doubt session, but do we get access to the recorded versions of such sessions? Because last two sessions, I think there was an upper limit of 100, and I think many of us were trying to join, and we were still not able to join because 100 people had already joined.
Right. So I don't know why that happened. My best guess is that Google enforced some restrictions on the number of participants. So previously, yeah, you can mute yourself. Thank you. Yeah, thanks. So yeah, so previously when I've conducted these sessions, there have been times where I've conducted sessions with more than 100 participants. So and I continue to use the same email ID to conduct these Google Meet sessions. So yeah, that's my best guess that maybe Google enforce some new restrictions on the number of participants. But yeah, to answer your question, the recorded videos are available, and if you go to the Swayam portal, if you go to this problem solving session recording over here, you will find the link to the recorded videos.
Thank you, sir.
Yeah. So Purab, to address your question again, yes, try to solve as many assignments as you can. That will contribute towards your final score. But if you have already missed a particular deadline, don't worry about it. Focus on the next assignments. Okay. Because I think there is some best few assignments that will be considered. I don't know the exact number, but yeah, you can ask this in the discussion forum as well. I think someone will be able to answer there.
Sir, and another doubt.
Mm-hmm.
Do we have any access to some previous years' question papers which we can refer to for this course?
Um, Question papers as such, unfortunately, I don't have access to, but questions from the previous iterations of the course is what we are discussing in the live sessions. So that should be of some help. But yeah, question papers, I've tried to look for question papers in previous semesters, but I haven't gotten hold of them. So yeah, unfortunately, I can't help you on that front. Yeah. So Srinivas, you had a question in one of the lectures. So I mentioned that for a full tree, the number of leaf nodes is so much. How do we get this? Um, okay, so I'll let you think about that. Okay. uh, or I'll also point you to some resources. Maybe uh, try to see or try to look up any Wikipedia page on um, what a full tree is, or a full tree. What do you mean by full tree? Can you elaborate on that? I'm also rusty on my concepts. Do you mean like a complete? Yeah. I see, I see, I see. So yeah, I would encourage you look up the Wikipedia page of such of a full tree and see if they have an explanation. If that is there, then great. But before that, you try to reason by yourself how many leaf nodes would there be. Okay, so think about it. Basically, you need to look up. Okay, so what is B in your equation? What is B and what is I? Branching factor. That's right. That's right. Mm-hmm. Mm-hmm. That's right. That's right. That's right. That's right. That's correct. So yeah, just think about it. How many internal nodes are you going to have in a full tree? And based on that, how many um, leaf nodes are you going to have? Think about it. If this doubt persists, we can take it up again in the next live session. Just remind me. Okay. I will also try to read up on it in the meantime. Yeah. Okay. 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 Which week is this? Which one? Practice example. This one, is it? Yeah, this one. Mm-hmm. That's right. Okay. Okay. Um, which of these trees is correct? Based on that, we'll see which is the path. We can just check the answers, right, and see. Oh, our guess is correct. So tree 2 is correct. So yeah. So here we are following SADG, right? So that should be the path, right? Mm-hmm. Yeah, yeah. Right, right. So the order in which, yeah, so yeah, the order in which we are exploring the nodes would be S, A, C, B, D, E, and then G, right? But the order in which we are, once we have found a tree, right, the order in which we are going to go from S to G would be dictated by S, A, D, G, right? If you look at the graph, S, A, D, and G. Yeah. Tree or tree or graph, whichever you feel more comfortable with. SCDG. But is that what we are encountering in the tree? In tree, there is no such way, right? Yeah. So I think you have to do a combination of tree and graph in that case, I guess. Yeah. Okay. Anything else? Okay, then if there's nothing else, then maybe we can close the session and yeah, Seth. Yeah. Mm-hmm. So we had seen that the lecture slides, you mean? So in week 3 it's there. Yeah, week 2 content is also in week 3, I think, as pointed out by one of your colleagues. Yeah, yeah. It's because we found beam search over here, right? So, yeah, yeah. Where I have to look at it. Maybe in this one. Okay, let's have a look at week 1 as well. Week 2, is it? Uh-huh. But that will be a video, right? That slide would be over here, right? Because here they are discussing state space search. Okay, maybe it's in week 1, but what's your question in general? Maybe that will give me some idea. Mm-hmm. Mm-hmm. So knowledge you can think as a set of facts, right? That you know. Um, and then what was the other thing? Experience. So experience helps you make sense of the knowledge that you have and also add more knowledge to your knowledge database, right? So for example, let's say your knowledge consists of the fact that if you throw or let's say there is a ball at the top of a mountain, okay, and your knowledge also contains that there is a force called gravity that pulls things towards the surface of the earth, right? This is your knowledge. Now when you go to the top of a mountain and throw a ball from there, you will actually see that the ball falls down from the top of the mountain to the ground. Yeah, so that is your experience in a way, you could say, right? And based on that, depending on the observations that you make, you can also add new facts to your knowledge database. For example, things like when you throw the ball from the top of the mountain, something like friction, air friction also adds to the process, and it slows down the process of the ball falling to the ground. Okay, so I just made up this example, but you could think of something more concrete as well. Does that make sense?
So basically, these two are interdependent. Like from knowledge you gain experience, and from experience you gain knowledge.
Yeah, that's correct. So Arya, to address your question, I am not a part of the WhatsApp group, and I won't be, mostly because I would prefer if all the doubts are resolved either through the discussion forum or through the live sessions, just simply because these two sessions are monitored by the official team, right? Whereas on the WhatsApp group, it won't be monitored by the official team. So, and also because these two sessions are public, so if you have some doubt, and suppose some of your colleagues also have the same doubt, they would also benefit from you asking the question. So, yeah. And anyway, the recorded sessions and the lecture materials as well as the slides are available to you through Swayam, so it should be okay, I suppose. Okay. Anything else?
So this is the first time I'm attending this live session. Can you please tell me how often the live sessions like these will be conducted? Is it once a week or?
It is so. This time we have two of us, two TAs who are conducting these live sessions. One of them will be happening on Mondays, 6 to 8 p.m., which is my slot. And then the other would be Saturday, I think. I can't remember the time exactly, but you can check up the announcements on Swayam and there you would find it. So it would be every Saturday at a certain time period and every Monday at a certain time period. And we would be discussing more or less the same things. There might be some differences in the questions and the approach we take, but yeah, you can feel free to attend either of those or both of those depending on your time. Yeah. Mm-hmm. Yes. Yeah. So Moksh, to answer your question, the questions, yeah, sure. So Moksh, to answer your question, the type of questions in your final exam would be very similar to the ones you are answering in the assignment. It will be, and I'm quoting the lead TA Bhaskaran sir over here. The final exam would be a shorter version of your assignments, combined across all weeks. No, no, values will be changed, of course. Question type will be same. Yeah, like for example, you might get a MCQ question or a multiple select question or fill in the blanks. But yeah, the graphs will be changed, the values will be changed. Yes. Mm-hmm. No, exact question won't be asked, I think. It will be modified only. Yeah. Okay. Anything else? If not, then let's close the session and see you next week. Thanks all for attending.